of kinetics. So kinetics is attached to or entails the idea of movement, motion. So movement, motion. So if we take a look at the kinetics of a reaction, we're looking at the movement or motion of the particles involved in the reaction. And rate just simply refers to how quickly the reaction will happen. Well, here we go. In order for any reaction to occur, the molecules must have what we call effective collisions in order to react. So I like to think about the idea of two boxers in a match. So the boxers can constantly collide with each other, throwing punches, but not every punch is a knockout punch. So to effectively knock out your opponent, your effective collision requires two things. Number one, the knockout punch must occur with enough energy or force. And that knockout punch, it can't land in any spot in the body but in a certain spot. You have to punch your opponent in that facial jaw area. So for collisions, for molecules for reaction, they have to happen with enough energy or force, and they also have to happen at a proper orientation for that knockout collision, effective collisions. So here we go. If you increase the number of effective collisions, you'll increase the rate of the reaction and the process will happen faster. Okay? The ways or the factors that affect the rate of the reaction. Number one is the nature of the substances. We can't control the nature of the substances. So ionic or salt solutions tend to react faster than organic molecules. Well, because there tends to be fewer bonds, and if it's in solution, then we already have mobile ions. They're already moving, ready to react. So ionic solutions react faster than molecules in general, especially organic molecules. Temperature. Well, if we want to increase the particle motion, then we increase the temperature, because temperature represents the average kinetic energy. It represents the average movement of all the particles in the sample. So the higher the temperature, the higher the average. All the particles are moving more. The more they're moving, you tend to increase the number of effective collisions, and having a faster rate, you increase the rate. Concentration, the molarity. When you take a look at these pictures, 3 moles versus 5 moles of solute. And when you take a look at the one with the moles of solute, there's a lot less room for all of those molecules to be moving in. So, as a general rule, as we increase the number of moles of solute we put into the reaction, we increase the number of collisions. Therefore, we should see an increase in the rate of the reaction. Now, pressure. Pressure only significantly affects the behavior of gases. If we increase the pressure on a gas, we will force that gas to occupy less space. So this idea right here, we have talked about in gas laws. This is Boyle's law, right? And so now if we put pressure on, those gas molecules have less space. There's less space to occupy. There's less distance between the molecules. So we increase the number of collisions between these gaseous molecules. We increase the rate. So surface area. surface area 1, surface area 2. We can increase the surface area of a sample, especially by like using a mortar or pestle, like turning it into a powder, so grind or crush. So think like powder. And what that does, as you can see, in the big chunk, contacts and collisions only on the outside. But as soon as we grind or crush, we have all of those same spots, but now we're getting to some of the places that were hidden. So we increase the contact points between the reactant particles. And so we increase the rate of reaction. We can also, like in industry, add a catalyst to a reaction. And a catalyst is a substance present during the reaction, but it does not participate in the reaction. The catalyst presence creates an alternate mechanism, reaction mechanism. So take a look. Here we have two houses. They're on opposite mountains, and the normal, regular, traditional pathway from house 1, you have to travel down the mountain, through the valley, the village in the valley, and then up the next mountain to get to that house. So this would be the normal pathway or mechanism. But this little village down here has gotten super busy, so the engineers built a bridge across the valley. So now there are two possibility pathways. You can still leave the house, walk down the pathway, work your way through the village, and head up to the mountain to get to the other house. Or you can leave the house, go across the bridge to get to the new house. So the bridge functions as the catalyst. And that catalyst bridge, it provides an alternate reaction mechanism. And think about the amount of effort it takes compared to going down one mountain, getting through the village in the valley and working your way up the other mountain, or simply going across the bridge. So that catalyst bridge supplies an alternate reaction mechanism by lowering the amount of activation energy. So it lowers the activation energy, makes the reactions happen faster. So let's take a look at a potential energy diagram that uses a catalyst. So here we go. We know the left-hand side platform represents reactants, the right-hand side represents the products, and the hill in between is the reaction mechanism of energy. So this is that hill, that's the normal. That's the normal reaction. But take a look. If we put a catalyst in, you still start at the reactants platform, but take a look at the size of the hill that connects the two platforms. And you still end at the products platform. So that red hill, this represents the reaction with a catalyst present. It takes a lot less effort to get to the products, reactants to make a products. So I want to just look at arrows here. So arrow 1, with or without the catalyst, did not change. The length of arrow 2 did change. Arrow 3 also changed. Arrow 4 did not change. Arrow 6, its length has changed, and then arrow 5 has not changed. So those are the arrow numbers. So the catalyst, what it doesn't change, 1, the PE of the reactants, 5, the PE of the products. So PE of the reactants, PE of the products, And because both of those remain the same, the delta H value also does not change. So that's the delta H. But the catalyst, what it does change is arrow 2, PE of the activated complex, 3, which is the activation energy, the forward activation energy, and 6, the reverse activation energy. So the activation energy for the normal forward is changed, and the activation energy for the reverse reaction. And if you notice, with the catalyst, all of those arrows' length became smaller. So that means we see a decrease in each of their values. And because each of these values decrease, we see an increase in the rate of the reactions. That's both for the forward and reverse. So both the reactions happen faster. So make sure you can draw a hill to represent the catalyst effect on a PE diagram.